introduction, and thank you for the chance of letting me talk here. I'm from the Max Planck Institute for Physics in Munich, and yeah, today I'm gonna tell you a bit how we try to approach the question of what is a dual amplituhedron. So this is the outline. I'm gonna mention first by what we mean by duality in the context of polytopes, where you have an understanding of what this dual formalism should be. Then I'm going to make a connection to a property of functions that is called complete monotonicity, and the theorem of Choquet, that's another people. And then I'm going to mention about notions of convexity and duality for semi-algebraic sets in the Grassmannian. And then in the end, I'm going to mention about how to interpret canonical forms of positive geometries as dual volumes. So let me just give you the definition of the amplitude. I think we already saw this morning, but for the sake of completeness, so we fix three positive integers k, m, and n, with n greater or equal than k plus m. We take a non-negative, positive matrix, which is k plus m by n, and then the amplituhedron is a semi-algebraic set in the Grassmannian grk, k plus m, defined as the image under this projection. So this is a linear map induced by z by right multiplication by its transpose. So it's the image of the positive or the non-negative Grassmannian grk, n under this map. And this is a semi-algebraic set inside this Grassmannian here. So I'm gonna try to keep it short. I know we have an apero, so I really wanna approach this question. So what is the dual amplituhedron? And this, let me mention first for k equals 1, we have an answer to this, because for k equals 1, the amplituhedron is a polytope. So it is in particular for m and n, it is a cyclic polytope with n vertices in projective M space. And what we mean by a dual volume representation is that we can take the dual of the cyclic polytope as, again, a full-dimensional polytope in Pn, and we can write the canonical function of the amplituhedron, the canonical function of this polytope, as an integral over the dual polytope by this measure here. So it's W is a point in the dual. We are integrating over the whole dual by this measure. And then you can notice that in particular this factor here is non-negative by definition. This is how the dual polytope is defined. So this comes from the fact that if we have a projective polytope, we can take the cone over it, the pointed cone over it. So here is a picture of this. If we have some square in the projective plane, we can take the cone over it. This will be a three-dimensional polyhedral cone. And we can take the canonical function of this cone and write it as a Laplace transform on the dual cone. The dual cone is defined by this, all the points and in the real space of dimension 1 higher, such that dotted with my original cone. So this is the Laplace type of formula. And if I integrate out a scale, if I integrate out this scale in Rn plus 1, that's the formula that I had before, where I had this denominator. So this is really what I mean by some dual volume representation of the canonical form. And the connection to this property of complete monotonicity arose recently because this property has been observed in many functions appearing in quantum field theory and building blocks of it. So this has been done by Johannes Henn, my supervisor, and Prashant Raman, who is sitting there in this paper. And let me give you the definition of complete monotonicity. So we take a cone, an open cone in Rm, and we take a function defined on this cone that takes real values. And we say that this function is completely monotone if all the directional derivatives with directions inside the cone of order r have some fixed sign. So in particular, this is telling that the function is positive on the cone. It has negative directional derivative with respect to every direction inside the cone. It has positive double directional derivative, and so on. So there is some positivity property on functions defined on cone. And this property is connected to this dual volume picture by a theorem due to Bernstein, Hausdorff, Wieder, and Choquet that states the following. So a function defined on an open cone is completely monotone if and only if there exists some Borel measure mu supported on the dual cone, such that we have Laplace transformation, a Laplace integral representation for f for every point inside the cone C as the integral over the dual, some Laplace transform of the measure mu supported on the dual cone. And in particular, because this Borel measure is because this measure is Borel, it is non-negative if it admits a density with respect to the Lebesgue measure. So what I'm actually integrating is I could think of this as some probability distribution on the dual cone, and this as a partition function for this probability measure. So, yeah, the connection between the complete monotonicity and positive geometry is really given by this theorem, because, for example, it proves that the canonical form of a polytope is completely monotone on the cone over the polytope, because we have this Laplace integral representation with measure equal to 1 on the dual cone. So we can really say that the canonical form of a polytope is completely monotone on the cone over the polytope with
So here we're talking about positivity, the monotonicity of the canonical form, but previously we were talking about functions.
Yes. I'm being a bit sloppy. I should say the canonical function. So I strip off the canonical, the measure.
Top form.
Yeah, okay. What about then other amplitudes for higher k, which are actually no linear objects? So this question of dual amplitude, I think, entails two questions. Because on one side we have a semi-algebraic set in the Grassmannian, which is, okay, it's full dimensional inside this Grassmannian, but we don't have really a notion of dual for a semi-algebraic set inside the Grassmannian, because before we were using duality of convex bodies or convex cones. It's a bit unclear how to define a dual semi-algebraic set in the Grassmannian, even though the Grassmannian is embedded in Brucker space, but I'll come back to this. The second problem is that even if we can write something along the lines of Choquet theorem, so if we can represent the canonical form of the amplituhedron as some integral over a dual semi-algebraic set with the analogous measure that is a generalization of that in projective space, how to find this measure? So these are the two questions. And approaching the answer for question one is hopefully a paper that will appear soon with Lizzie Pratt, a student of Ernst Sturmfels in Berkeley. So we worked about notion of convexity for amplituhedra, and this led us to study some polytopes, which we called exterior cyclic polytopes. So the notion of convexity we consider is very naive in some sense. So we take a real algebraic, real projective variety embedded in a real projective space, and we take a semi-algebraic set inside the variety. And then we define the convex hull of the semi-algebraic set inside the variety as the intersection of the variety with the convex hull in the ambient projective space. This is a very naive way to define something like the convex hull operation for semi-algebraic sets inside a variety. And then we say that a semi-algebraic set is extendably convex if it is equal to this notion of convex hull inside X. So this notion has been considered by Busemann for sets inside the Grassmannian in the 1960s. One can consider it, I think, more general in this setting. So here is a simple example. Well, first of all, it boils down to the usual notion clearly in projective space. And here is a simple example. So X is given by the vanishing locus of this polynomial of degree 4, which I already fixed in some affine chart. So it's this shape here, it's this curve here. And I take, in the first case, the semi-algebraic set here, given by this red part. And this is extendably convex because if I take its convex hull in this affine chart and I intersect it back with my curve, it's equal to itself. But this is not true anymore if I take, for example, my semi-algebraic set to be this part here, because the actual convex hull will intersect in more than my semi-algebraic set. This was just one example. Right, and considering this notion of convexity, or asking, is the Amplituhedron convex in the Grassmannian with respect to this notion, led us to consider a polytope. And this polytope is defined by lifting the Amplituhedron map, which is between the Grassmannian. We lift it just between the respective projective, the respective Plucker embeddings. This is the map at this point is just a linear map given by the exterior Kate product of Z. And we define the exterior cyclic polytope as the image of the non-negative orthant in here. So this would be a convex polytope in this projective space here. And this we call exterior cyclic polytope, and it also depends on 3 parameters as the Amplituhedron. And it depends in particular, I mean, as the Amplituhedron, it depends explicitly on the positive matrix Z.
Sorry, is this a cyclic polytope?
No, for k equals 1, it is, but it generalizes the cyclic polytope. It's not just a cyclic polytope in general.
Can I choose Z so that it is a cyclic polytope, or?
Ooh, that I don't know. I think we didn't explore this question.
I think you get more facets though, right, for higher k than that.
Yeah, probably just even the count of probably just from the factor you can say no, I guess. But maybe for some specific choices.
Is it independent of that?
No, it actually depends. Even in the cases where we know that the Amplituhedron is independent, or the combinatorial type of the Amplituhedron is independent on Z, the exterior cyclic polytope instead depends on Z. However, this polytope is interesting to us because it's exactly the convex hull of the Amplituhedron inside the Plucker embedding. This is why we consider this. So in general, we have an inclusion, because of this, we have an inclusion of the Amplituhedron inside the intersection of the polytope with the Grassmannian. And the Amplituhedron is extendably convex, so this is the notion of convexity I defined before, if and only if this inclusion is actually an equality. So then we were considering when is this the case. So for m equals 0, let me just give you a trivial example. Both the Amplituhedron and the exterior cyclic polytope are just a point, the same point. So it's the Amplituhedron is extendably convex in this case. For m equal 1, this is not the case, because here is a picture of an Amplituhedron for m equals 1, k equals 3, and n equals 5. So this is known to be a union of the union of bounded chambers of a hyperplane arrangement, in this case in P2. And the exterior cyclic polytope is kind of the convex hull. I mean, it is the convex hull of it, and it's strictly larger than the Amplituhedron itself. So for m equals 1, the Amplituhedron is not extendably convex. So maybe one could ask if at least for m equals even this is the case. Well, that was too ambitious, but for m equals k equals 2, we managed to prove that the Amplituhedron is indeed extendably convex. So it is the intersection of GR24 with the exterior cyclic polytope for those parameters. And it also coincides with the intersection of GR24 with another polytope that I'm going to briefly tell you about now. So this is what we call the truncated exterior cyclic polytope. So it is taken from the exterior cyclic polytope by forgetting all the facets that are not Schubert. So we only keep the Schubert facets of the exterior cyclic polytope, where a facet is Schubert if it's projectively dual to a point on GR24 in this case. So this will be in general, the C tilde will be a bigger polytope than C. But nevertheless, we can show that this equality is true. And this C tilde polytope is somehow related to the dual of the exterior cyclic polytope, where it intertwines with what is known as the twist map. So this twist map was defined by Fomin and Zelevinsky, I think first in the context of cluster algebras, and it constructs, in our setting, it allows to construct a new positive matrix W from the positive matrix Z by taking this triple wedge product of the neighboring columns of Z and then associating it to actually a vector and a 4 vector. And one can show actually that they showed, I think, in the original paper that this map maps positive matrices to positive matrices. And we could argue that the C tilde polytope is really equal to the dual of C.
Is the involution property obvious in the polytopes? If you do twist twice, 2 twists, then you do the same thing.
From the point of view of polytopes, well, I guess like double duality maybe.
But one's tilde, one is C, that's why maybe I didn't know some definitions of what.
Yes. No, I don't know. I didn't think of this. I mean, I'll definitely rely on the fact that tau is an involution. Then,
up to some notations. Yeah.
Yes, in this case, it's a proper involution for this specific choice of parameters. So it's really, I'll rely on that. Because I want to define a notion of duality in this context.
Sorry.
Yeah.
Do you have some results for m equal to 4?
No, not in this sense. We provide a lemma that could allow to prove that. In principle, there are some technical things to be checked about this intersection of the polytope with the Grassmann. If one shows that it is a regular semi-algebraic set, then the quality follows.
Sorry, could you go back to the previous slide?
Yep.
So which of these results do you know are false for, let's say, even M?
So we think, because of conversations with Nima, that for m equals 6, this equality is not really true, because if this equality were true, in particular, the algebraic boundary of the Amplituhedron would consist only of linear divisors, which, talking to Nima, it doesn't seem to be true, but we didn't work out an explicit example, so I don't have too much to say. For m equals 4, because algebraic boundary is believed to be this vanishing of II plus 1, JJ plus 1, it seems very plausible that one can show it very similarly. There are just some technicalities that I mentioned that are missing. For m equals 6, I don't know, it seems that it starts getting a bit wilder.
Sorry, Leo, before you take a follow-up on this question.
Sure.
So couldn't it be that some of the facets come from the Grassmann, and then it would be linear, even in the m equals 6? Even if you had the equality and for the m equals 6 Amplitude?
Yeah, I guess that could happen. In principle, it could happen. I mean, I would imagine that if you intersect a variety with a convex body, usually part of its algebraic boundary really comes from the variety itself.
Yeah.
It's kind of interesting that it does not for Amplitude somehow. Yeah, I don't know. It's but for the M equals 6 amplitude, I think the statement is that there are codimension 1 boundaries in the part of the algebraic boundary of the amplitude is not linear, which is different though from what we just said.
So what about the second statement? Does it make sense even for arbitrary m, the second proposition you have?
For arbitrary m,
Let's say for higher m even.
for higher m, could be. We explored higher k. I mean, just a couple of examples, and it seems to work. For higher m, I don't know, but it seems plausible. Yeah. Right, so I want to define a notion of duality now for semi-algebraic sets in the variety, very much in spirit to the notion of convexity. So we take again the semi-algebraic set in a variety X, and we define the extendable dual of the semi-algebraic set to be the intersection of the variety with the convex dual of the semi-algebraic set itself, which is the same as the dual of its convex hull in the ambient projective space. So these duality symbols are really just the convex dualities in the real projective space. So by the way, by this I mean you take an affine chart, you do this as usual Rn, and then it has been shown that it's independent of the affine chart you choose. Unless you're up to the fact that your hyperplane does not cannot intersect the semi-algebraic set. Right. So according to this notion of duality, the non-negative Grassmannian is self-dual, because the non-negative Grassmannian is by definition the intersection of the Grassmannian with the simplex, and the dual of a simplex, or the standard simplex, is again the standard simplex.
How the boundary poset maps? I mean, is it the same? I mean.
Yeah, I don't know actually the level of the poset. I think of that. Right. So with this notion, I can try to define something that I would like to call the dual amplituhedron, and for A equals M equals 2, by the intersection result I presented before, we have this sequence of equalities. So we know that this exterior cyclic polytope is the convex hull of the amplituhedron. So the dual amplituhedron, according to our definition, is taking the dual of the exterior cyclic polytope and intersecting with GR24. By this relation with the C tilde polytope, this equality holds true. And again, by the intersection theorem, I end up with an amplituhedron, which is already something interesting, but where now the positive matrix has been changed to this parity dual matrix, or this twisted matrix. So the extendable dual for K equals M equals 2, it seems to give us back an amplituhedron, but with different positive matrix, what in physics would correspond to parity duality, so in exchanging MHV sector, which is K equals 2 with MHV bar. And here, because it's a workshop, I thought I could present some open problems related to this work with Lizzie. So I said that the combinatorial type of the polytope will vary for Z, but we observed that for generic Z, at least the F vector is constant. It would be nice maybe to prove this. This is related to your question, so can we generalize this relation between the dual of the exterior cyclic polytope and the twist map?
Sorry, what do you mean generic? Z?
Generic, I mean really that's away from a variety in the space of positive matrices. I mean that.
Would an example be of a non-generic thing?
Yeah, when some minors of Z vanish, then the combinatorial some faces of C collapse.
But we're assuming Z has positive maximal minors.
Yes, still assuming positive maximal minors, but some smaller minors. The vanishing of some smaller minors could change the combinatorial type. Yeah. Then, okay, extendable convexity for different M would be interesting. And this relation between duality and parity duality for M equals to an higher K that we checked for some examples to hold true, it would be interesting to approach. And also I think it's interesting to people that work with triangulations and tilings of the Amplituhedron to relate these to triangulations of the exterior cyclic polytope, at least when we have the intersection result. And for people interested in adjoints, the same. So what is the relation of the adjoint to the polytope to the adjoint of the Amplituhedron? Can we actually use this to prove that the Amplituhedron is a positive geometry, using that the adjoint of a convex polytope is really. So let me now go back to problem 2, which was assume that now, let's say our notion of duality is the right one, such that we can write some dual volume representation like this. What should be the measure? We're working on some simpler cases, so not really Amplituhedron, but we're considering non-linear positive geometry. This will also appear more or less soon, hopefully. Canonical forms as dual volumes. And the idea was to work out concrete examples like the pizza slice, which we learned before today that it's actually an amplituhedron where you send the number of particles n to infinity. So it's still related to the amplituhedron somehow. But it's really a semi-algebraic set bounded by a conic and a line. The convex dual of this set is this one, which is the convex hull of the conic and the 0 point, which is dual to this line. So this pizza slice is a positive geometry, and its canonical form is given by up to some constant 1 over the equation of the line times the equation of the conic. Has no numerator. And we could compute something like the Choquet representation. So we could show that the canonical function of this pizza slice has a Laplace integral representation over the dual with a non-trivial measure supported really on the dual cone of this, where the measure is now non-trivial. So it is equal to 1 only on this part here, but inside the convex hull of the conic, it is basically some logarithm. And if you plot it, so here I'm plotting mu over the disk, it's non-negative. It vanishes on the boundary of the conic, but then it goes up to 1, and it is equal to 1 on the remaining part. It's actually smooth, even though it's piecewisely defined.
So the boundary is kind of discontinuous?
The boundary, 0 and then jumps to 1. Yes. But in the interior, it's perfectly smooth. And so the fact that it is non-negative by the Bernstein-Hausdorff-Wieder-Choquet theorem tells us that the canonical function of the pizza slice is Cm on the cone over the pizza slice. So this computation and these questions led us to some interesting connections to hyperbolic polynomials. So this 2 slides before, this polynomial here turns out to be hyperbolic. And this has then connections to hyperbolic PDEs or PDEs with constant coefficients or to spectrahedra and to exponential varieties. So I don't have time to comment more on this point, but I will be happy to do so if the rest of the week. Then we have more examples. So before, the pizza slice didn't have any numerator, any adjoint. But we also worked out, for example, like a proper pizza slice bounded by the conic and 2 lines. And now it has an adjoint which interpolates these residual points. And again, so the dual of this semi-algebraic set is this set here goes out to infinity because we put the origin in the boundary of our region. And we get again some logarithm as a measure which can be checked to be non-negative. And by general arguments we can do, we know, for example, that the canonical function of a nodal cubic, which is 1 over the equation of the nodal cubic, is also completely monotonic by this connection to hyperbolic polynomials. So there exists a non-negative measure supported on the dual, which is this thing here. But to compute it is already it's already hard enough, and it may contain some elliptic integrals. So we conjecture that. So open problems along this direction are, well, more generally, which positive geometries have completely monotone canonical forms? Seems to be related in particular to convexity. Then it would be interesting to study more general properties of the measure, even if we cannot compute it, like where should it vanish, what singularities, if it has any, should it have, or what is the transcendental degree, if it's some iterated integral. It would be interesting also to see how triangulations work for nonlinear geometry. It's not so clear even for the pizza slice. If you triangulate the dual, it corresponds to some very weird triangulation, or it's probably not even right to call triangulation of the original space. And then how to compute more generally these measures? Can we connect to D-modules techniques? And then very importantly, can we define some notion of complete monotonicity for functions defined on varieties like the Grassmannian? And right before dinner, I would just want to mention that we are working with Johannes Prashant, Yaroslav, and Martin Lagares, who's now starting a postdoc, I think in Queen's Mary. And we observed that many amplituhedron related quantities, which involve integrated quantities from negative geometries, for example, when one can actually integrate the forms coming from positive geometries and obtain finite functions, that they share this complete monotonicity property once you parameterize the points in the Grassmannian by positroid parameterizations. So it's very fascinating. There should be some generalization of the notion of complete monotonicity also for these kind of functions on the Grassmannian, and maybe at some point we'll be able to know what the dual amplituhedron is. That's all.